Energy, the foundation of everything in the universe, the force that fuels galaxies, stars, and planets, the thing that makes us who we are, what allows us to walk, think, develop, and illuminate the world, the fuel of airplanes, machines, computers, every device in our homes, every food we eat, everything. Energy. We talked about planets, we talked about the laws of the universe, general relativity, gravity. We said E equals mc. We talked about countless equations. We talk about quantum physics, and we will talk about it even more. All of them are magical formulas that explain what's happening around us. But there is one thing we still haven't talked about. We haven't talked about what lies behind all of this, about that force we inevitably see in every formula. And without understanding it, many things will not fall into place. We haven't talked about energy. So really, what is energy? Like time, it remains abstract. When asked suddenly, we can give explanations, interpretations, but truly, what is energy? Let's clarify this subject and talk about energy. As we said, from the chocolate we eat to supernovas, from electronic devices to heat. Let's take a look at this magical force underlying everything, the efforts to make sense of it, the equations, and the people who dedicated their lives to it. And as always, let's go a little bit back in time, to the moment when the answers to this question were first sought. And even before that, when we look at human history, we see that we've used many ways to harness energy for our benefit. When we lit fires to keep warm, built mills, and raised sails across oceans, we used different forms of energy. But about 300 years ago, something incredible happened. Humanity began using steam engines. Machines whose invention dated back thousands of years finally had their true potential discovered. Tasks that normally required dozens or hundreds of people could now be done with a single steam engine. Humanity didn't first encounter the fear of robots taking our jobs recently. This transformation began centuries ago. But this change, this revolution, would transform the entire world. Before going into more detail, I want to mention another name. As you know, the stories behind developments are, in my opinion, just as important as the developments themselves. They give us a more holistic perspective. So let's talk about Gottfried Leibniz. More than just a diplomat or a scientist, Leibniz was someone who dedicated himself to understanding the mechanism of the universe. He believed that the universe we live in was an incredibly powerful machine, created by a force, and that to understand the logic of the creator, we needed to understand how machines work. If we understood machines, we could understand the universe. To him, philosophy, religion, and engineering were deeply intertwined. In the late 17th century, this led him to investigate a very simple yet profoundly important question. What happens when objects collide? For example, when two billiard balls hit each other. According to Leibniz, there was a transfer of force. Something passed from one object to another. To him, this force was something real, something living. He called it living force, something shared between two objects during a collision. With this idea, Leibniz thought of the world itself as a living machine. He believed that God had placed a living force into the universe at creation, and that this force would remain constant forever. The challenge, of course, was defining it. Soon, he would provide a mathematical description of this force and reach a fascinating conclusion: the explosive power of gunpowder. He observed that the living force inside it was released as flame and steam. And he believed that if this force could be harnessed, humanity would hold an extraordinary power. He himself worked on this idea, capturing, storing, and using this living force, and he knew it could be done in many different ways, by transforming force, by converting heat, for example, into extremely useful forms. He understood that humanity's power could be multiplied indefinitely, that the labor of one person could become equivalent to that of hundreds. Unfortunately, these ideas remained theoretical in his time. They were far ahead of their era, and as always, proof was required. That proof would come in the 19th century with steam engines. This was exactly what Leibniz had envisioned. It's sad that he never lived to see it. Steam engines. Human progress moves step by step. but steam power was a massive leap. With steam, we could do things we couldn't even imagine before. More importantly, it told us a great deal about the living force Leibniz spoke of, and about how the universe works. Strangely, even though we used steam engines, very few people understood what this power truly meant, or what it revealed about the cosmos. One of the most important of those who did was Sadi Carnot, another name we rarely hear, yet one that fundamentally changed the world. Originally a soldier, Carnot was born in France, which had been defeated by England, a nation rapidly advancing thanks to steam power. He understood very well how crucial steam power was. Whoever possessed it could do anything, so to pull his occupied country out of this situation, he got to work. In 1824, he wrote what would later become legendary, Reflections on the Motive Power of Fire. In fewer than 56 pages, he explained how all heat engines work. In essence, he said this: every heat engine consists of a hot source and a cold sink. Heat behaves like a fluid flowing from hot to cold, and this flow can be used to perform useful work. From this, he derived a fundamental principle. To make a heat engine more efficient, you must increase the temperature difference between the hot source and the cold sink. This astonishing discovery would underpin all future technological progress. For example, car engines are far more efficient than steam engines because they operate at much higher temperatures. Jet engines are even more efficient for the same reason. Beyond this, Carnot had uncovered a deep secret of the universe. Nature operates through energy exchange between hot and cold. With this discovery, Carnot effectively founded a new field of science, thermodynamics, the science of energy, entropy, and heat transfer. That is why he's known as the father of thermodynamics. Yet, like so many others, Carnot never saw the impact of his work. He died in 1832, at just 36 years old, during a cholera outbreak in France, leaving behind an extraordinary legacy. Throughout the 19th century, studies on heat, motion, and energy accelerated. As machines were built and engines were analyzed, astonishing connections were discovered. Different forms of energy, once thought to be completely separate, were actually deeply connected. Scientists could now calculate exactly how much of one type of energy was required to produce another. For example, the energy needed to heat 30 milliliters of water by 1 degree Celsius is exactly the same as the energy required to lift a 12.5 kilogram mass by 1 meter. The strange implication was this: mechanical work and heat, though seemingly different, were simply different forms of the same thing: energy. This became the first law of thermodynamics. It states that energy cannot be created or destroyed, only transformed. And it implies something more. There's a fixed amount of energy in the universe, just as Leibniz had predicted. In a steam engine, we don't produce energy. We merely convert heat into motion. But one question remains unanswered. How does this transformation occur? And more importantly, why? Here, Rudolf Clausius enters the story, who introduced the second law of thermodynamics. According to Clausius, not only is energy conserved, but it also follows strict rules. Heat flows only in one direction, from hot to cold, never the reverse. That's why your coffee cools down. It seems obvious, but this simple observation reflects a fundamental principle of the universe. Clausius described this process mathematically and introduced a new quantity, entropy. Entropy changed everything. It tells us that during heat transfer, entropy increases. It measures how energy spreads out. In its simplest form, it says this: every system tends towards disorder, and this is irreversible. Everything that emits heat participates in this irreversible process. Your cooling coffee and the universe itself obey the same rule. To truly understand entropy, scientists had to go further. By the 19th century, the idea that the universe was made of tiny, constantly moving particles began to take hold. But how did this connect to energy? Why does order tend towards disorder? Here, Ludwig Boltzmann enters the story, who assumed that everything, me, you, buildings, the universe, was made of atoms. He proposed that when an object heats up, its atoms move faster. At the time, even the existence of atoms was debated. Yet Boltzmann went further and derived the brilliant equation explaining entropy statistically, without tracking every atom individually. He showed that when a hot object cools, energy spreads from an ordered state to a disordered state. His equation, one of the most important in scientific history, essentially says this: disorder is far more probable than order. Everything tends towards chaos. Disorder is the fate of the universe, and of us. Entropy even helps explain aging and death, which is why it's inspired so many philosophical discussions. But here's the key question. If everything tends towards disorder, how did life emerge? The answer lies in the very same process. Life exists by exploiting energy flow, by using the tendency towards disorder. Just like a car engine, it converts ordered energy and fuel into motion while releasing heat and noise. Our bodies work the same way. We consume energy-rich food, release it into disorder, and use that process to stay alive. So perhaps the lesson is this: we can't stop entropy, but we can slow it down. As long as we transform energy, as long as we act, we can delay decay. The same applies to life. If we want to survive, we must stay in motion. So transform energy, get up, do something. And as always, until next time, I'm glad you're here. Much love.